Module 8, DNP3 over LAN, WAN, and IP networks, extending utility communication beyond serial links. 8.1 Motivation for IP-based DNP3 transport. DNP3 was originally deployed over serial and radio-based communication media, reflecting the dominant utility infrastructure of the 1990s. As utility networks evolved, the need arose to integrate DNP3 into LAN, WAN, and enterprise IP environments without altering its application semantics. Key drivers included expansion of fiber and Ethernet in substations, convergence of operational technology, OT, and IT networks, cost efficiency of IP-based transport, requirement for long-distance, high-speed communication, integration with corporate and regional control centers. DNP3 over IP emerged as an encapsulation strategy, not a protocol redesign. Tasher 8.2 Transport independence of the DNP3 application layer. A foundational principle of DNP3 is transport independence. The DNP3 application layer remains unchanged regardless of transport medium, preserves identical object models, function codes, and behaviors, assumes no guarantees beyond what the link layer provides. When operating over IP networks, DNP3 frames are simply carried inside IP packets, while application semantics remain identical to serial implementations. 8.3 DNP3 over TCP/IP. Encapsulation model. In TCP/IP deployments, the DNP3 link layer frame is encapsulated within a TCP payload. TCP handles packet delivery, ordering, retransmission, flow control. The DNP3 protocol stack remains intact above TCP. Operational characteristics: reliable, connection-oriented communication, reduced need for link layer confirmations, improved throughput and reduced latency compared to serial links. TCP-based DNP3 is well suited for substation LANs, control center WAN connections, fiber and microwave backhaul networks. Add 8.4 DNP3 over UDP IP. Rationale for UDP usage. In some deployments, UDP is preferred due to lower latency, reduced protocol overhead, predictable timing characteristics. UDP-based DNP3 relies more heavily on DNP3's native reliability mechanisms. When using UDP, DNP3 link layer CRCs remain critical. Application confirmations are often enabled. Retry and timeout strategies must be carefully engineered. UDP transport is typically used in controlled environments where latency sensitivity outweighs retransmission overhead. 8.3 Substation LAN integration. Modern substations frequently deploy Ethernet LANs connecting protection relays, bay controllers, RTUs, HMIs, data concentrators. DNP3 operates seamlessly over these networks, enabling high-speed polling, efficient event reporting, consolidated communication infrastructure, coexistence with other protocols. DNP3 commonly shares Ethernet infrastructure with protection protocols, engineering access tools, time synchronization services. Isolation is achieved through network segmentation rather than protocol modification. 8.6 WAN and enterprise network considerations. Wide area deployment challenges. When DNP3 traverses WANs and enterprise networks, additional considerations arise: variable latency and jitter, packet loss and congestion, firewall and routing constraints, network security boundaries. Despite these challenges, DNP3 maintains deterministic behavior due to its explicit transaction model. Addressing and routing. DNP3 source and destination addresses remain logical identifiers. IP addressing and routing are handled entirely by the network layer. There is no semantic coupling between DNP3 addressing and IP addressing. This separation preserves protocol clarity. 8.7 Impact on polling and event behavior. Polling over IP. Polling strategies over IP networks typically increase poll frequency, expand event class utilization, reduce reliance on integrity polls. Higher bandwidth availability allows finer-grained data acquisition. Unsolicited reporting over IP. Unsolicited responses over IP benefit from faster delivery, reduced contention, improved confirmation reliability. However, unsolicited traffic must still be carefully controlled to avoid overload. 8.8 Performance and scaling implications. Throughput improvements. Compared to serial links, IP-based transport enables larger fragment sizes, faster response cycles, reduced polling latency. This allows masters to manage significantly larger device populations. Scaling limits. While IP removes many physical constraints, scaling is still bounded by master processing capacity, event buffer sizes, database update rates, control center architecture. DNP3's deterministic request-response model ensures predictable scaling behavior. 8.9 Interoperability and backward compatibility. A critical feature of DNP3 over IP is full backward compatibility. IP-based masters can communicate with serial outstations via gateways. Mixed media networks operate transparently. No changes are required to application layer object handling. This enables gradual modernization without system replacement. A reliability model over IP networks. Even when TCP provides reliable delivery, DNP3 retains application layer confirmations, object-level validation, explicit error reporting. This redundancy ensures that semantic correctness is preserved even if transport guarantees fail or are misconfigured. 8.11 Architectural implications for modern utilities. DNP3 over LAN WAN allows utilities to converge SCADA and automation networks, leverage standard networking infrastructure, centralize control and analytics, extend automation across geographic regions. Crucially, this evolution is achieved without altering the core DNP3 protocol, preserving decades of operational stability. Summary of IP-based DNP3 operation. DNP3 over IP represents an extension of reach, not a change in identity. Same data model, same control semantics, same reliability philosophy. By decoupling protocol behavior from transport medium, DNP3 remains a durable and adaptable foundation for modern network utility automation systems. Module 9, DNP3 Interoperability, Standardization, and Compliance Framework. 9.1, Interoperability as a core design objective. Interoperability is the central reason DNP3 achieved widespread adoption in utility automation systems. From inception, DNP3 was engineered to allow devices from different vendors with different internal architectures to communicate reliably without custom integration work. Interoperability in DNP3 is achieved through open, publicly available specifications, strictly defined protocol behavior, standardized data models, controlled evolution of the standard. This approach prevents fragmentation and preserves long-term system viability. 9.2 Open specification and vendor neutrality. DNP3 is a non-proprietary protocol governed by an independent user consortium rather than a single vendor. Key characteristics: publicly accessible protocol documentation, no licensing restrictions on implementation, equal participation of utilities and vendors in governance. This ensures that utilities are not locked into a single supplier and can evolve systems incrementally. 9.3 Role of the DNP user group. The DNP user group serves as the custodian of the DNP3 standard. Its responsibilities include maintaining and publishing protocol specifications, issuing technical bulletins and clarifications, managing backward compatibility requirements, coordinating interoperability initiatives. The group balances innovation with stability, ensuring new features do not break existing deployments. 9.4 Controlled protocol evolution, backward compatibility mandate. One of the highest priorities in DNP3 evolution is preservation of compatibility. This is enforced through additive feature introduction, non-breaking changes, strict deprecation rules. Devices implemented decades apart can still communicate successfully. Incremental enhancement model. Rather than wholesale redesigns, DNP3 evolves through technical bulletins, optional feature extensions, clarified interpretation of existing behavior. This minimizes risk in operational environments. ICON 9.5 Recommended Protocol Subset. Purpose of the subset: DNP3 is a rich protocol with many optional features. To ensure consistent interoperability, the DNP user group defined a recommended protocol subset. This subset specifies mandatory function codes, required object groups and variations, required behaviors for masters and outstations. Interoperability impact. By conforming to the recommended subset, vendors ensure baseline compatibility, utilities reduce integration uncertainty, system engineering effort is significantly reduced. Devices implementing beyond the subset may still interoperate as long as the core subset is respected. 9.6 Implementation levels. DNP3 defines implementation levels to manage complexity across device classes. Level 1, basic read operations, limited object support, minimal memory and processing requirements. Level 2, expanded object sets, event handling, additional function support. Level 3, advanced features, full event reporting, unsolicited responses, extended control capabilities. Levels allow resource-constrained devices to participate without sacrificing interoperability. Tag 9.7 Object and Variation Compliance. Standardized object definitions. Every object group and variation in DNP3 is formally defined, precisely encoded, semantically constrained. Devices must correctly parse and generate objects they claim to support. Handling unsupported objects. If a device does not support a requested object or variation, it must return a defined exception response. It must not silently ignore the request. This explicit behavior prevents undefined system states. 9.8 Test Procedures and Conformance Verification. IED Test Procedures. Standardized test procedures define request-response sequences, timing expectations, error handling behavior. These tests validate that implementations conform to protocol rules rather than vendor interpretation. Third-party verification. Independent organizations provide conformance testing services, compliance certification, interoperability validation across vendors. This external verification increases confidence during system integration. 9.9 Multi-vendor system integration. Practical interoperability outcomes. When vendors conform to DNP3 standards, masters can communicate with diverse outstations, devices can be added or replaced without redesign. System upgrades do not require protocol changes. This is critical in utility environments where equipment life cycles span decades. Reduction in engineering effort. Standardized interoperability reduces custom driver development, protocol translation gateways, site-specific engineering. The result is faster deployment and lower lifecycle cost. DACON 9.10 Coexistence with other utility protocols. DNP3 is designed to coexist, not dominate. It can operate alongside other utility communication protocols, enterprise data systems, legacy field protocols. Interoperability frameworks allow protocol translation when required while preserving DNP3 semantics upstream. 9.11 Deterministic behavior across vendors. Interoperability is not limited to syntax. DNP3 defines timing behavior, error semantics, control execution rules. This ensures that a command or data request behaves identically regardless of vendor implementation. Number 9.12 Long-term system stability. Through open governance, controlled evolution, and formal compliance mechanisms, DNP3 achieves decades-long backward compatibility, predictable system behavior, confidence in multi-vendor deployments. This stability is a defining reason DNP3 remains a cornerstone protocol in utility automation systems worldwide. 9.13 Summary of Interoperability Framework. DNP3 interoperability is not accidental. It is engineered and enforced through open standards, defined subsets and levels, formal test procedures, independent verification, strict backward compatibility rules. Together, these elements form a robust framework that enables reliable, scalable, and future-proof utility communication systems.